right, let's take a step back. So we've been down there in the lands of permutation. Let's now focus on the largest part of the world, the lands of queries. There are quite a few of them in there, but we'll go through them quite quickly. So one thing you can extract out of a collection is some sort of value. For example, the simplest one is probably count, that takes beginning and end and a value and returns how many times this value occurs in the collection. There's accumulate, that makes the sum of the elements of the collection, calling operator plus, or any custom function you'd pass it. In C++17, there's reduce that appeared, that does practically the same thing as accumulate, except it has a slightly different interface. It can accept to take no initial value, and it can also be run in parallel, but essentially it's the same as accumulate. And transform reduce takes a function and applies that function to the element of the collection before calling the reduce. Partial sum, well, it sums all the elements starting from the beginning to the current point of the collection. So here, partial sum would return a collection with, in the first position, what was in the first position of the original collection, and in the second one would be the first one plus the second one. In the third one would be the first plus the second plus the third, so on and so forth. In C++17, there's inclusive scan, exclusive scan, transform inclusive scan, transform exclusive scan, which have interesting names, let's say. Well, inclusive scan is the same thing as partial sum, except it can be run in parallel. Exclusive scan is the same thing as inclusive scan, except it doesn't include the current element. So for example, with exclusive scan, the second element would be equal to the first element of the original collection. The third one would be 1 plus 2. The fourth one would be 1 plus 2 plus 3, and so on and so forth. And the transform versions of those two guys take a function, apply it to the collection, and then perform the including/exclusive scan. Inner product makes the inner product of the collection, which is a multiplication of the counterparts elements, and then summing that whole thing. Adjacent difference makes the difference between every two neighbors in the collection. And sample, appearing in C++17, takes something that can that can generate random numbers, and it takes a number, say n, and it produces n elements of that collection selected randomly. Apart from querying a value, we can query a property. Well, there's all of, any of, and none of, which are really useful in everyday code. All of takes collection and predicate, returns if all of the elements satisfy that predicate, any of if at least one element satisfies that predicate, and none of if no element satisfies that predicate. Now, what do you think all of returns with an empty collection? What do you think? Fred? True. Does everyone agrees with Fred? Yeah, that's true. Any of on an empty collection? Yeah, false. None of? Come on, there's only two possible answers. Yeah, true. Absolutely. That was querying a property on one range. We can also query a property on two ranges, which is essentially different ways of comparing them. The simplest way to compare two ranges is to see if they have the exact same contents. So the element would be equal 2 by 2, and it would have the same size, and that's what std equal returns. It returns a Boolean. Now, if we'd like to know if the two collections contain the same element, but not necessarily in the same order, that is permutation, also returning a Boolean. Now, we can also compare ranges and say which one is smaller than the other one. To define smaller, we could go with size, but that's not very precise. There's another way to do that, is going back to the alphabetical lexicographical ordering, right? Like in this example, I've used characters, but that can be with any type that has a comparison operator. You can see on this example that the left collection is smaller than the second one, than the right one, if they were in a dictionary, right? Even though it's longer in terms of size, it would come before in a dictionary, and that's what lexicographical compare returns in the form of a Boolean. Now, the last way to compare two collections is to traverse them both and stop whenever they start to differ. That's what mismatch does, stud mismatch, and it returns a pair of iterators pointing to the respective position where they start to differ in the two collections. Now, a classic thing to extract in a collection is a position, like looking for something. Well, to look for something in a collection, there are essentially two ways to do that. It depends on whether the collection is sorted or not sorted. If it's sorted, we can use a binary search. If it's not sorted, we have to go all the way through from the beginning. Let's start with the not sorted case, because it has the lower number of algorithms. Well, the simplest one and very famous one is find. Std find takes a value, a begin and end value, and returns the iterator where pointing to that value. Now, or end if that value is not found. Now, it has a sort of like twin brother that's much less famous, but quite useful as well, and it's called a JSON find. And that returns the first position where two adjacent value occur and are equal to the value searched. So JSON find takes a begin and an end and a value and returns the first position where two of those values appear in a row. On the sorted side, we are not really looking for a value, because searching for a given value could be at several places, and since it's sorted, they would be lumped together, right? So in this example, if we're searching for orange, we're actually looking for a subrange that could be empty if orange is not there at all, and that's what equal range returns. To search in a sorted collection, we use equal range. There are other algorithms that sort of like look like it, lower bound and upper bound, and they only indicate positions to insert elements. Like if I were to insert a new orange, at the left of the existing orange, I would use lower bound, and at the right of the existing orange, I would use upper bound. And there's this guy, binary search, that returns a Boolean, which is a bit unexpected, because it takes a beginning and end and the value, and only tells you whether it's there or not, but doesn't tell you where it found it. And it uses a binary search, which is a good thing. Now, we've been looking for one value in a collection, like orange. We can also look for a range of value in a collection, like looking for the first occurrence of a subrange in a big range, like looking for that range on the left in the big range. To do that, there's an algorithm that has a very bizarre name because it's called search. I don't know what you think, but for me, search is almost the same as find, except find says that it will find it, right? And search says it will try to find it. But search has nothing to do with find. It searches a subrange into a range. That's not the best name. I think the most curious name in the whole STL library is what follows, which is looking for a subrange but starting from the end. It's called find end. That's good to know, isn't it? And what we can search in a subrange is any of the value in the little range, finding its first occurrence in the big range, and that's find first of. And finally, we can search for a relative value, which is the largest one or the smallest one. That's max element or min element, or both. Min, max element that returns a pair of iterators pointing to the max and the min, the min and the max element. Right, we've been around the largest part of the world. Now we're going to move in my favorite place. It's the glorious county of the algorithms on sets, because they're glorious. Well, what's a set to begin with? It includes a std set, but not only. In C++, what we call a set is any sorted collection. So a std set is sorted and is a set, but a sorted vector, for the purpose of the STL algorithms, is also considered as a set. Set difference, which is my favorite algorithm, takes two sets and returns the elements that are in the first one, but not in the second one. And its interface is like that. It produces its output via an output iterator. I like it so much because it's useful all the time, and it's also in linear complexity. And it would be easy to implement in quadratic complexity, but it's in linear complexity because it uses the fact that the input are sorted, and also its output is sorted. Set difference has siblings. Set intersection, that returns the element that are both in A and in B. Set union, that returns elements that are in A or in B, so everyone. Set symmetric difference, which is, I think, the longest name. Yeah, it's the longest name in the whole library. Fun fact. That returns the elements that are in A and not in B, and those that are in B and not in A. Includes, that returns a Boolean that indicates whether all the elements of B are also in A, and merge. That takes two sorted collection and puts them together into one big sorted collection. Oh, that's it. What was that? Too short. Okay, let's take a step back. We've been in the most populated regions of the world, all over here. We now have just these parts, small parts to cover. So maybe we'll take an hour after all.